Yep, so yeah, as this talk is going to be focusing a lot on Windows and on bypassing and also finding out exactly how EDRs tend to be implemented at the low level. Primarily because, as mentioned, EDRs up and coming, especially a lot in like financial sectors and places like that, they tend to actually have multiple EDRs. They'll have like Cylance, Carbon Black, CrowdStrike, Falcon, all of the types, and they'll do their own testing on them and implement them as well. And one thing I haven't actually noticed much of is a lot of research into how EDRs actually do what they do. We find a lot of information on like antiviruses, for example, on how they do heuristics and stuff like that. And there's hundreds and hundreds of blogs on bypassing AVs and the like, but not so much with EDRs. So when I managed to get my hands on a couple of these products, I took the time to actually chuck some of them in IDA, do some reverse engineering, and answer some of the questions I've had regarding these. And one important reason why I did this in the first place as well is not only because of the lack of current research in this area, but also because of the fact that I have gone against some of these EDR products on, say, red team engagements before, and they definitely raise the bar in terms of how you operate. They'll detect a lot of the general post-exploitation techniques you would do on a host, things like, you know, running mimikatz, grabbing hashes, doing thread injection, process injection, all those types of attacks. Yeah. Just a bit about me. I'm a consultant at Context, as mentioned. That there is my Twitter handle, which is feel free to DM me after this if you have any additional questions. That's probably the best way to reach out there. Otherwise, if you find me afterwards, feel free to come up. Yeah, so some of the goals that I intend to achieve here is to firstly go through what is an EDR, what makes up an EDR, what are their general capabilities before we dive into something more technical for anyone who has not had much of an introduction to EDRs before. Afterwards, we'll actually analyze some of the internal details of EDRs in regards to how they perform their sensing operations and stuff like that on a Windows operating system. And then I'll actually demonstrate some complete bypasses. What I mean by this is bypassing their defensive the defensive operations really that block or terminate or even log your actions. And this isn't really targeting any specific EDR. This is kind of a generic thing based on the EDRs I've tested, based on the fact that there is only so many ways they can operate or do what they do on a Windows system, because they have to abide by the laws of the Windows operating system. And I'll be going through, there's a few live demos through here, depending how much time I have. So there'll definitely be a demo of the bypasses and some other interesting Windows internal stuff that relates to how EDRs operate. Yep, that's just a general flow of what we'll go through. Like I said, we'll start with an introduction. As I mentioned, why EDRs? Most of the biggest point to take away here is that they do raise the bar quite significantly, as we'll take a look at now. So I've got a few snippets here of what you would see on their website, say Cylance's website, Carbon Black, CrowdStrike. You can see they all advertise AV-like behavior, so they typically say, you know, you can uninstall your AV and install this instead. They do offer those, like, you know, your basic signature checking stuff, but they also have zero-day protection, or what they call zero-day protection, along with more behavioral-based detection. And I think that's one of the main things I've gathered that separates an EDR from your typical AV, is that EDRs don't focus so much on who you are, but more on what you're trying to do. So they typically would log and block and terminate and stuff specific actions rather than, say, trying to detect based on signatures and stuff, which they do have some support for. Technical details, you won't find much technical details, if anything, on their website. Most of it's like, you want to hear more, send us an email and we'll send a sales guide to you, which as an independent researcher is not going to happen. Or even just a researcher for a security consultancy is going to be hard to happen. And most of them also do not offer free trials, or they say they offer free trials, but then you click on it and then once again they want you to email them so they can get a sales guide to you. As opposed to like lots of AVs where there's heaps of free versions you can just download off the internet, you know, Avast, whatever, and give a run. Or even if you did want to pay for them, like Bitdefender and that, they're relatively cheap, easy, you know, 99 bucks, whatever, you got it. These, not so much. Not so much because of just money, but also because they assess whether you're someone they want to sell to. All right, taking a very simplistic look at the prevention capabilities here. This is just an example to give you an idea. So on one side we have just AV running, other side EDR running, with just an obfuscated or recompiled mimikatz just to bypass signature checks. And as we can see on the antivirus side of things, you know, ran mimikatz as admin, got debug privileges, and dumped hashes from LSASS, which will contain, you know, usually password hashes. On the other side, we have EDR running. It allows me to start up mimikatz. It allows me to get debug privileges. But as soon as I try to actually dump anything from LSASS, it just terminated the process. That's why it dropped me back into the just normal command prompt. And that would have also been logged back to a server. So you can see here the key difference between them is detecting the actual behavior. Up to the point where I actually tried to touch LSASS, the EDR didn't really care what I was doing. Yep. If you take a look at the admin panels for these EDR products as well, you'll find that a lot of their power comes from the verbosity of their logging. You can see, I've got a couple examples here where they list, you know, the first one, application Werfault.exe attempted to open some other process by calling this specific function, and whether that was successful or not. And then on the next one, it logs the IP and the location of the IP and all of those information. One thing I want to kind of give you guys here as well is when you're reverse engineering anything really, in this case a security product, it's not all about chucking it into a disassembler and viewing the assembly bytes. There's a lot of reverse engineering that you can do just based on the functionality exposed or the output that these products give you. From looking at this, there's one particular thing that jumped out at me, which kind of gives me an idea of how it might be detecting these operations. And that was kind of this part here, where it notes the exact function that an application called. So open process would be a Windows API function. And the very fact that it's able to report on that means it needs to have visibility of me calling that function. And there's only so many ways on a Windows operating system that you can get visibility of specific Windows NT API functions being called. So that alone kind of gives you an idea of what it may be doing in the background, or where you might want to start looking if you do chuck it into something like IDA, which we'll get to later on. Yeah, so based on the output, I know generally if it's able to block and terminate actions, then somewhere between our process and the actual operating system that does these actions, the EDR has to kind of be like the man in the middle there. It has to know what operations the process is trying to call, and it has to be able to block it or terminate it before it succeeds. So before the request actually goes to, say, the Windows kernel or whatever to do that actual operation. On the other side here, we also see more of an admin panel from one of these EDR products, where you can say, if something tries to scrape memory or, execute a fileless script or inject code, it's able to terminate the process or block the process or whatever. So that tells us that, yes, it must be sitting somewhere in the middle. Another point I want to mention, just while we're on this, is there are a lot of other configuration weaknesses and all of those type of things that you find in pretty much any other product that are applicable to EDRs. You can see that you can specify things like application paths. So, you change the path name or you rename it or copy it elsewhere and it's not going to work. By not working, this detection rule is not going to work. That's why they offer the ability to do hashes and stuff like that, but then you might be able to append null bytes to the executable. So there's always kind of specific configuration issues there. I may touch on some of them, but for the most part, I'm going to be focusing on the kind of generic behavior that the EDRs perform, so that we have more of a generalized bypass for these types of products, or even just an understanding of how they all work. The general components that kind of make up these is there'll be typically a server hosted somewhere that will communicate with the endpoint agents that will be installed on various workstations and servers. And those agents will comprise of userland agents that will do a lot of the kind of AV-like behavior and also give you like a little UI pop-up and stuff like that. But it'll also have kernel components like network drivers and file system drivers to intercept whenever someone writes to disk and actually handle a lot of the actual meat of the application. So one of those is, the filter driver, which will sit between the actual file system drivers, so like the NTFS driver or the FAT driver, and between that and, say, anything else really from the kernel land. So in this example, you have a userland process that's calling the NT-open-file function on a file. So anything to do with like file system stuff, generally creating files, reading files, deleting files, will go through the EDR's filter driver. And that will be the point where it's like, okay, do I want this operation to succeed or not? And it can determine that before it passes it off to the operating systems like NTFS driver to actually start reading in the file. One use of this may be to protect its own files from being deleted from disk. You might try to delete it from disk, it goes to kernel land, the kernel land driver will be like, nah, that's my file, reject that operation. Another feature is to just keep note of what you're accessing and then telling its userland EDR binary to just scan that if you're going to access it. There's various settings for EDRs to, say, not allow something to execute until it's done scanning and things like that. The thing about EDRs as well is they are highly configurable. So there'll be actually a couple of weaknesses I'll go on, just some key ones about the configuration. But that does leave a lot of room for user error. All right, we'll jump into some of the more internals of these now. We'll get into a few live demos, or I'll bring up examples of these. This is probably one of the key areas of this presentation to really understand how these products are implemented, how they're able to sense. We saw from some of the output earlier that they're able to know the specific functions that application tried to call and what binary called that. We'll look into how it's able to detect that and how you're able to also find this out, I guess. So one key part that the Windows operating system allows kernel drivers to utilize are callback routines. So there's various ways that you can insert a callback. Essentially, to give an example, the first one, right, PS set create process notify routine. What that essentially is you'd have a kernel driver, you would call this function, and you'd give it an address of your own function and say, hey, whenever a process is created, let me know. So then whenever a process is actually created, whatever function you passed it will be called back and notified, and also passed some other details about the process. They've got that for loading of images, creation of threads, for handle creation, process handle operations, thread handle operations, registry operations, and there's various others that also have more obscure names that are a lot harder to kind of figure out what they do. There's a bit of research gone into identifying the various callback mechanisms that exist on Windows. If you search for that on Google or whatever, you'll find some current research on that field, which is always interesting to see. But the primary function that I've noticed EDRs use is the PS set create process notify routine, which will make more sense shortly as to why they do that. But I'll just give you a quick example of how you may find this. So if I just quickly open up IDA. So I've just opened up the Windows NT operating system kernel, which is in C drive Windows System 32. And if you look at the exports, you'll see the set create process notify routine. That jumps to PSP set create process notify routine. And somewhere down here, we have this address being called. What this value is here, I have symbols, which makes life easier. This is actually an array, and this is going to be an array of callback structures for every driver that's registered a callback. So we can actually visualize this on my VM. So this VM has an EDR currently installed on it, and I'll show you how you can actually view the callbacks that are registered on that operating system. All right. So I'll just go to local kernel debugging. Now if I go ps set. So this is the exported function from the NT kernel that we saw earlier. We saw the jump here. Ignore the symbol name, and the symbols are a bit broken on this machine. That's fine. So now I disassemble from there, and we're looking for we're looking for this layer to R15, where then it's accessed later on, to find the address of the array. All right, so it's here. We got Leah. The symbols are broken, but it doesn't matter. Leah, that to R15, and then R15 access, like we saw earlier. So if I dump this as, or display it as a pointer values, you can see we've got 1, 2, 3, 4, 5, 6, 7 callbacks, process notifier callbacks currently registered on this system. Now these are off a partially opaque structure called X callback structure or something like that. It's partially documented. I think the React project, React.rs project, has also done some documentation work on this to try and find out exactly how you can get the driver function that was registered with the callback from this structure. But yeah, that's just to give you an idea of how you can actually find the callback routine arrays, and we'll actually leverage this a bit later on in another fun example. But it's the same process for finding the address of the other callbacks as well. Now, one reason why, if you want to know if a process is started and things like that, drivers have to rely on these callback mechanisms is because there's Patchguard on Windows. And for anyone who's not familiar with Patchguard, Patchguard was introduced, I don't remember exactly when, maybe XP, Service Pack 2 or something like that, somewhere around there, to kind of minimize the shifty behavior in the kernel that a lot of drivers, both legitimate drivers and malicious rootkits would perform. Because a lot of those kind of shifty operations would actually result in lots of blue screens. In user land, if your application does something wrong, say you get a seg fault or something, your user land process crashes, and you got, process.exe stopped working. Yeah, that's fine, you just close it. When something like that happens in kernel land, you get a blue screen of death and your entire machine crashes. So not a fun time. So what Microsoft implemented is this Patchguard, which will actually validate a lot of the core structures of the Windows operating system in the kernel. And it does this because lots of products used to modify kernel structures in the Windows operating system. For example, a rootkit might say whenever a process, or for example, a rootkit might hide its userland process by getting the list of processes, because whenever there's processes running on Windows userland, there's like a linked list of every single process running. So what a kernel rootkit might do is find its process and just unlink it from the chain. So when task manager goes to, say, enumerate that list, it doesn't see your unlinked process, so it's hiding your process. That's one rootkit reason of modifying the Windows kernel. Patchguard will actually detect that now and crash the system and be like, was it like critical structure modified or something like that as the reason for the crash. And the way Patchguard works is that it's kind of sprinkled throughout the kernel, so you can't easily turn it off. And there'll be various pseudo-random events, like maybe a timer ran off, or you plugged in a USB port, or you made an internet request, or just random, pseudo-random stuff will happen. And that will actually wake the Patchguard thread that will verify some critical structure. And if that, there we go. If that critical structure has been modified, it will crash with the error code critical structure corruption, which means it crashed because a Patchguard found something malicious or just wrong with the critical structure. Otherwise, it will just go back to sleep and it will be broken again to verify some other structure at some other point. This is actually a very important part or determinator as to how EDRs work. This is because the way API functions kind of work in Windows is like this. So above the dotted line is user land, below the dotted line is kernel land. So say mimikatz wants to dump memory from Alsace. It will call read process memory, which is exported in like a kernel.32 stub DLL, and then that'll eventually just be forwarded pretty much to NTDLL. And NTDLL will have NT read virtual memory, and that will do a syscall operation. So what a syscall operation is in kernel land, you have this syscall table. And what this is, it's pretty much a table of IDs and function pointers. So read virtual memory might have a specific ID of, 3A, and then write virtual memory might be like 3C or something. Every particular function will have a unique ID. And NTDLL will put that ID into a register and then transition the context to kernel land, where it will look up that ID into the syscall table and find the kernel function that will actually do that operation. So when you call NT read virtual memory, the reading of the virtual memory happens in kernel land in that NT bang NT read virtual memory function I have at the bottom there. So what a security product might be enticed to do is just replace the NT read virtual memory function in kernel land with its own function, so that whenever you call read virtual memory in user land, it transitions to kernel land perfectly fine, and then the syscall table lookup happens, and instead of going to the Windows function, it goes to your function that you've put in there instead. And then you verify whether you want that function to actually go ahead or not. If you want it to go ahead, you can just jump execution back to the original pointer, or you can just reply, operation failed or whatever you want. But you can't do that with Patchguard, because Patchguard will verify the syscall table has not been modified. So if you replace a function pointer in the syscall table in kernel land with your own function pointer, at some point, Patchguard's going to verify that structure, it's going to see it's modified, and it's going to crash. So as a result of that, that limits how an EDR can actually intercept and understand what API calls and what operations an actual application is calling. So they do the next best thing. They target this part in user land, which is kind of the last part before it jumps to kernel land. The reason why this works is because Patchguard doesn't really touch user land, it verifies kernel structures. So what an EDR will do is it will actually patch NTDLL in memory to redirect, instead of doing a syscall to the kernel, it will redirect code execution to their own injected DLL. And then their DLL will verify the operation in user land, determine if it's something they want to go ahead or not, and then if it is, they'll do the syscall and jump it in. If it's not, then they'll just reject the operation. Well, first they'll log the operation, do all sorts of stuff, and then reject the operation. This is kind of probably the key part here. This is the core of how pretty much, at least all of the ones I've seen, and the EDRs would actually intercept what you're doing, how they log what operation you're doing, as we saw before with the open process example, or how they might block and terminate applications, which is kind of forced due to the limitations of Windows again. So if we were to visualize this, what they would call their zero-day prevention, essentially by just hooking the API calls in user land. So if we dump NT write virtual memory from the NTDLL, which is loaded up into virtually every process, you'll see it moves 3A into EAX and then does a syscall. So what this means is that 3A is going to be the syscall identifier for the write virtual memory function, which is going to just write into process memory. And then it's got the syscall operation to transfer context to the kernel, where it does that lookup I ran through, and then returns. What this actually gets turned into, if you look at this on a system with an EDR installed, is that instead of the moves and the syscalls, you've got a unconditional jump to some other DLL, in this case, CTI user. CTI user in this case is the DLL of the, or userland DLL that this particular EDR product injects into your process. And then at some point in that user DLL, if they like what you're doing, they set up the syscall and they jump back to kind of in the middle there where you see the 0F05 in hex, which is going to be the syscall instruction. So if it likes what you're doing, it's just going to syscall as normal. If it doesn't like what you're doing, it's just going to terminate. Straightforward. So how does it actually do the hooking? If we look at how it actually does this, we can see that first, well, we create a process. In this case, we're creating malware.exe. It can be whatever. And then the operating system will be like, all right, I'm chucking the untouched, fresh on disk copy of NTDLL into your process. And since the process was created, the kernel is going to go through the PSP create process notify callback arrays, and it's going to call back any kernel drivers that registered to be called back. The EDR driver obviously would have been registered for that, and they'll get notified. And at this point, the EDR driver actually hands off the rest of the work to its userland process. And it says, hey, userland EDR process, I want you to patch NTDLL in this process ID. So at that point, the EDR process will do things like process open, virtual protect X to remove the read-only protections on NTDLL. Then it'll write process memory to overwrite or patch NTDLL. It'll inject its own DLL into there. And as we saw before, patch NTDLL to jump to its own DLL. And then it will do virtual protect X again to restore the original protections on that DLL. And this is probably the most important part of my talk right here on this one slide. Just because it actually covers the whole flow of how it does the injection. And this injection part is how an EDR product has its eyes, really. How it's able to see what you're doing. And we'll actually abuse this weakness, more like this approach, later on. When we start looking at the self-protections that these EDRs may come with, so some of the common protections, a lot of them are actually optional. One is having an uninstall code requirement, which is optional and off by default, which is interesting. So generally, if you're admin, so you need to be admin, but if you have admin on a machine that has an EDR installed, you can just call the uninstaller and it just uninstalls itself. That's nice. But obviously, if they have this little tick box ticked on their web panel that says, yes, require a code, then before you can do that, it's going to want a code to before you can uninstall it. But there's something interesting about that I'll go into later as well. They prevent deletion or modification of the installation folder and files and the actual EDR files themselves, so you can't just be like dragging this driver into the recycle bin. And it also prevents termination of their own process. Pretty standard stuff. But interestingly, there was actually a few protections that I wouldn't have thought were unreasonable, but weren't there. Things like obfuscation. In fact, not only was there no obfuscation, but a lot of the EDRs had debug print messages throughout all of their code, which may not have been enabled unless you set a registry key, but the very fact that you can view them when you chuck it into something like IDA makes reverse engineering these products a lot more straightforward. They don't have in-memory self-integrity checks. If you modify any part of the EDRs themselves in memory, they typically don't care. The ones I tested certainly did not care. And also, whenever you fail and uninstall, the ones I tested also didn't seem to log that operation or that failed operation, which is also interesting. And one of the reasons why I think this is because of the kind of lack of research that's gone against these EDR products, which I think I've actually seen more of a pickup on research in EDRs in the past few months, which is a good thing. But previously, or even now, there's just not many resources on anything to do with the technical details or analyzing EDR products. One common way that I see very frequently when anyone tries to ascertain the effectiveness of an EDR, be this a client who's determining which EDR product they should go for, or someone on a red team engagement where they grabbed a copy of the EDR with permissions and they're trying to find out how they may go against this on their next engagement. What I've seen very frequently is they'll have their bucket of techniques and they'll install the EDR and they'll just pick up random techniques and just start throwing it at the EDR and seeing what sticks. It's an approach, it's a quick approach, and you most commonly will find something that manages to stick and you're like, all right, I'll just do that. But they're typically very limited or very specific to like this specific operation you managed to get through by dumping LSASS through Task Manager instead of mimikatz or something. And you don't really understand why that worked. You can't use any of that weakness for another technique because you don't know why it worked. You just know it works for this case. So you have that case as just like a little technique you keep tucked away somewhere. But in terms of actually finding technical details as to why that worked, to try and find out the underlying weakness or abuse that in other ways and things like that, there's a very limited amount of research there. And one key point to that is the fact that it's hard enough to get a copy of an EDR in the first place. Like I mentioned, free trials are going to be very difficult to get. Even if you have money, they want to know who you are or if they should sell to you first. You can't just throw money at it. Maybe if you had enough money, I don't know. Yeah, so those types of things lead me to believe that these EDRs weren't developed with, say, as much strictness around security or as much focus around security as, say, a anti-cheat driver may be compiled with. If you look at things like, I don't know if anyone here has looked at anti-cheat drivers before, things like BattleEye's driver and things like that, they typically implement like heaps of crazy protection mechanisms. They'll have their own virtual machine to virtualize their code and make it very difficult to actually understand anything. When you chuck into IDAR, they'll do control flow graph obfuscation and anti-debugging stuff and all types of security protections. And that's because in the kind of game hacking scene, game hacking is an old thing, right? There's always been a back and forth between game hackers and game developers, especially when you talk about competitive games, Counter-Strike, Battlefield, things like that. They're always releasing new types of anti-cheat drivers and code like that. So they've been thoroughly battle-tested to the point where they've had to implement these protections, otherwise their product is completely useless. But in terms of EDRs, it doesn't seem like they've been pushed enough to the point where they have to start thinking about security at that level yet. Which is why we see things like Dbg Prints Everywhere. You know, this is just an example of things like looking through it and seeing, say, even if you're not the best reverse engineer in the world, you start going through some functions and you don't know what you're looking at, and then you see something say, hey, this registry callback failed. So then, you know, all right, you must be in the registry callback function or some function that handles registry callbacks. So you go back up to that function and you might mark it, registry callback function, question mark, come back to it later. And that really helps out in terms of reverse engineering these things without taking up weeks or months or years. All right, now we're going to get into some of the more fun stuff here about lots of the weaknesses that exist in these EDR products. There'll be a few live demos. Some of these are due to oversights by EDRs, so some of them are specific, while others are generic ones based on the restrictions imposed by the operating system that don't really have much of a mitigation, or at least they haven't employed mitigations for these yet. So, as I mentioned, uninstalling the EDR, I mean, this is a very low effort one. If you've, post-exploitation, you want to do things like maybe they have KeyPass and you want to inject into KeyPass and wait for them to unlock it, or you want to dump LSASS and things like that. So you got admin through credential reuse or some other way. EDR not going to help you there. So now you're thinking about, okay, just uninstall the EDR. Like I said, password is optional. You might say, all right, they've ticked and enabled passwords. How secure is that? Sometimes these products don't allow you to have secure passwords, which is kind of interesting. The reason why for this is they'll have things like, here's an example of a company-wide uninstall code. So there'll be an uninstall code typically for a specific endpoint. So you can only use this code for this one machine to uninstall. But they'll also have company-wide uninstall codes so that you could use this uninstall code across any machine in that organization. And if we look at this, I went through and generated a bunch of these, and they all had limited character sets. They were all just alphanumeric in capitals only. They had a static password length of just 8 characters. So it's brute forceable. With off-the-shelf tech, it's brute forceable. And when you're looking at the way it actually, in this specific example, I looked at the way how fast it could process an uninstall code, and it was very quick. It wasn't using anything like, I don't know, what's a slow hashing mechanism, like Bcrypt2 or something like that. So you could easily take the uninstaller offline and brute force that portion of code that does the uninstallation checks, the code check, and once you find a successful one, you go back onto the machine and do it. And the reason you can actually do this off the machine is because A, you can copy the uninstaller from the computer. You can't delete it or modify it, but copying it out is no problem. And the so the way this specific one works is it's got this long ass code in this text file in the same folder, and it'll do this calculation on your uninstall code and then just do like a comparison. And that text file is readable by all users, so you can just copy everything you need off that system, brute force it offline. When you find it in like a week or something, you just go back on and you uninstall it. And since it's a company-wide code, you can uninstall it everywhere, which is kind of crazy. And one interesting thing I saw in this particular product is maybe an indicator of where their priorities currently lie. So there's also a code when you install the product, much like a serial key or something. When you compare the security they've put into the uninstall code to the security they've put into the install code, it's interesting, right? Suddenly we have 12 characters. They've got special characters. They've got numbers in there. They've clearly gone, all right, we need a secure install code. And then when it comes to the uninstall code, they're just like, whatever works. Interesting. Possibly another side effect of the fact that they just haven't been hit hard enough. Yeah. All right. So for this particular example, if I have time later, I might go through the demo of this, but it's very straightforward. So I've got a snippet of the uninstaller here, and we can see it calls what I've named the code check function. That will actually do the code check and return the success or not success value into EAX. And then if it's successful, it'll jump to the other highlighted, can you see the highlight? Everything looks white on the screen. Okay, but both of those blocks are highlighted green. So what that means is once it checks if the code's successful, it'll jump to that other little box at the bottom there and then continue the uninstallation process. So you can actually falsify the code check result, because this product, if you try to start up like a debugger, like Windows debugger, and then attach to a different process to then modify that process, it'll terminate you, it'll kill you, whatever. But if you start Windows debugger and then you start the process that you want to modify as a child process, it's a lot less restrictive, and you can actually start patching it in memory that way. So what you can do is you can install a debugger or just write your own code to load up the uninstaller, and then just patch the uninstaller in memory to always jump to the successful control flow little area. And then at that point, once it jumps there, it will continue the uninstallation process and it will work. And the reason why this works is because the uninstall code is only checked in the uninstaller binary just that once. After that point, it will communicate with the driver, tell the driver to start removing its callbacks and tearing itself down, and it'll do all of that perfectly fine without needing an uninstall code. It's only this one part in the uninstaller that just checks for it. Another interesting thing is removing a callback. I did this initially as a fun exercise to write a Windows kernel driver, which was fun, to essentially load up my kernel driver, find the callback array as I ran through earlier, and then just null it out. At that point, as we've determined before, the EDRs rely on that to actually have visibility as to what's going on. If they lose that visibility, they can't block or terminate or log anything. I'll actually go through this in a quick example. The practicality of this is very limited because to load up a driver, you need to be admin. But if you have admin, typically you can load up a driver. Even if you wrote the driver yourself and it's an unsigned driver, there's lots of ways to get an unsigned driver into memory. The easiest way is find a driver that's signed that has a vulnerability. There's been a few from Capcom and from a few other places as well. Oracle's had a couple. VirtualBox has definitely had a few, and they always come out with more like every week. So if the old one doesn't work, you just use the one next week. And the interesting thing about that is even if a driver's certificate has been revoked because they know it had a vulnerability and they patched it in a new one, you can still load it up in Windows as long as the signature was valid at some point. They don't do certificate revocation checks in the Windows kernel. So you can use a driver that's vulnerable that was signed 10 years ago where that signature is like no longer valid because it's been revoked, and you can still load that up with no worries on a normal Windows 10 system. And then you can exploit that to load up your unsigned driver. So just to save time, I'll do it the quick way in the Windows debugger here. So we've already determined that this is the array of callbacks. I'll try to run mimikatz here, see what happens. Yeah, we can see I was just terminated, and that would be logged to the server. Now, I believe the last time I went through this one was the address of the EDRs one. It doesn't really matter. You can knock them all out. I've knocked them all out and nothing happened. Nothing bad happened. So that's always a good sign. But as with you do anything in the kernel, you could always stuff something up and then like 2 months after the machine's running, it will somehow crash because of that one thing you did like 2 months ago. All right, I've knocked out that entry. Let's see if I was actually correct. And it was that entry. No, you're not going to see my personal passwords here. No, okay, it wasn't that entry. Let's try again.
Need to sacrifice another goat.
It's definitely one of these entries.
You know it's a nice day outside, right?
One more.
God damn it.
It's got to be this one. Knowing my luck, it's going to be the last one.
It's always the last one to try.
That's some good fast typing under pressure, man.
There we go. Yeah, so as you can see, it definitely relies on that process callback mechanism. And all of this you can find, I did it the manual way in Windows Debugger, but you can write up a driver to do it, or if you have a way to execute kernel code from admin, which hint, there's generally a few ways to do that, because Microsoft doesn't really consider admin to kernel much of a security boundary. Yeah, you could easily do that. I'll just restore snapshot. And jump back in. All right. So that was just a kind of a bit of fun in showing how it's implemented, get a bit of understanding, show you through a live demo that it actually does work that way. I'm not just up here lying to you all. But as some of you probably noticed or thought of as soon as I showed you how it patches NTDLL, there's a much more generic, easier way to bypass all of these hooks, and that's through not using their patched NTDLL. All you need to get through is the syscall part, because that's the part that it patches on the NTDLL. There's two ways you can do this, or at least these are two of the ways you can do this. One way is to just have inline assembly in your program to manually do the syscall operations whenever you want to do something. That's a lot of effort. I mean, you don't have to do it that way. And also, syscall IDs are subject to change between various versions of Windows. Even like a simple update might change it. So that's very targeting a specific, you would have to know what version specifically of Windows your target's running. The easiest way to bypass these things completely is to just load up a unhooked version of NTDLL. Because the way EDRs patch NTDLL is they patch it in memory, not on disk. So the on-disk version is perfectly fine. The result of this is a complete bypass. You will have to do a little bit of Windows API foo magic here, just because you can't call load library and just point it to NTDLL and be like, load this into my memory, because Windows will be like, you already have NTDLL in your memory, I can't load it twice, not going to happen. There's a couple ways you can get around that. The first way is copy NTDLL to a different folder and rename it. That'll work, but it requires manual intervention. You have to do that whenever you go on a computer. It's a bit of a pain. The easiest way to do it is load up NTDLL in memory manually yourself by just reading it into a buffer as a file. You can be stealthy, and if you're familiar with the Windows API, you can do things like create it as a section in memory, so it kind of blends in with the other DLLs that are loaded. But if you're not that familiar with the Windows API, you can just literally go the very easy way and create a buffer, mark it executable, dump NTDLL into there, just reading it from disk into that buffer, passing the PE structure, because on Windows it'll be PE or like PE32 plus, which is like the 64-bit structure, which is fully documented. Microsoft has it documented on MSDN. Various other people have blog posts where it's documented, and you want this so that you can find the exported functions you want to call. So if you want to call NT read virtual memory to read the memory of a different process like ALSAS, you want to pass the export table of NTDLL that you've just loaded up, find the location of NT read virtual memory, and then just use that as your function pointer whenever you want to read virtual memory. Or you can overwrite your current pointer, which currently redirects to the EDRs DLL, and just patch that again yourself. So you go from NTDLL fresh in memory, NTDLL patched with EDR, NTDLL patched again with your own hook. So you're essentially hooking NTDLL that was hooked by EDR to go to your fresh NTDLL. All right, the result of this is a complete bypass. I'll do a quick demo. Yep, didn't work. I have one version here that's compiled to use a fresh version of NTDLL, and that works. No other modifications needed. And the very last part, if you want some code to play around with, there you go, have at it, whatever, test your solutions. I use this as an excuse to play around with the Microsoft Detours library, which was fun. But it's just a little POC for you to play around with. And that's it.
Everyone thank Christopher Vella.